So we're going to do one more mean value theorem example, and you'll need to just write this down on paper. So we're actually going to find the place where the mean value theorem applies to this function, f of x equals x cubed minus 2x squared, and we're going to look on the interval 0 to 2.5. So we're going to find the value c in the interval 0 to 2.5, where the f prime of c equals the f of b minus f of a over b minus a. So the first thing I'm going to do is the left-hand side. I'm going to figure out what my f prime of c is. So it's just going to be my regular derivative, but with c's instead of x's. So my regular derivative would be 3x squared, but we'll say 3c squared minus 4c. So that's the first thing I'm doing. The second thing I'm going to do is this part. So step 2 is right here. Step 1 was doing this part, finding the derivative and plugging c in. So step 2, we're going to find f at 2.5, and we just plug that in our calculator. So 2.5 cubed, subtract 2 times 2.5 squared is 3.125. And f at 0 is just 0. So we're doing f at 2.5 subtract f at 0 over 2.5 subtract 0. So 3.125 subtract 0 over 2.5 subtract 0 ends up being 1.25. So now we need to set these equal to each other. We're going to say 3c squared subtract 4c equals 1.25. Bring everything to one side. And then this is likely not factorable, so we're going to use the quadratic equation. So c equals the opposite of negative 4. So minus b plus or minus b squared minus 4ac all over 2a. Then we do the discriminant part first. So 16 subtract 4 times 3 times negative 1.25 is 31. So 4 plus or minus root 31 all over 6. And we're going to get those two answers in our calculator. So the first answer is about 1.59. The second answer, I believe, will be out of our interval because we're subtracting root 31, which is definitely bigger than 4. So negative 0.26. So that's out of our interval. So 1.59 is our answer. So we're going to say f prime at 1.59 equals 1.25. So let's go ahead and take a look in Desmos and see if this makes sense. So we'll put in our original function, which was actually x cubed. I started to put in the derivative. So x cubed subtract 2x squared, and we're going to restrict this to just be between 0 and 2.5. So we're just looking at that section. We have our secant slope, which was 1.25, and we'll just do x. We can just do x minus 0 plus 0, or just 1.25x. And we think that if we do our f prime at our critical number, I'm going to go ahead and put in the exact answer, which was 4 plus the square root of 31 all over 6. Oh, that is also 1.25, which makes sense. We can also do y equals f prime of c multiplied by x subtract c plus f of c. That is our equation of a tangent line. We can add this slider for c and set it between 0 and 2.5. Let's make the step 0.01. And now we can kind of move this slider around until we can see visually that it looks like it is parallel to that secant line, but we can also just go ahead and set the c value to our exact number, which was 4 plus the square root of 31 all over 6. And we can see right there that it's a perfect match, that our secant slope and our tangent slope are equal to each other.